Welcome to Lab 4, Oscillations. The purpose of this lab was to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring and predict the motion of the spring mass system by using a computer model created using the fundamental principles. The result of the lab is that the model closely predicts the motion and energy of the spring mass system. Tracker was used to analyze the video of the spring mass system. The mass was tracked in each frame, and here's the video that was used. The X and Y positions were recorded in the bottom right of the screen, and the position versus time is graphed here. The position data was saved in a CSV file that was later used to input into the VPython code. To create the model, several calculations had to be made. These calculations were based off of the fundamental principles, including the momentum principle, Newton's second law, and the energy principle. The energy principle states that the total energy of the system equals the sum of all of the energies of the system, which in this case includes the kinetic energy, the potential energy of the spring, and the gravitational potential energy. Creating the code. Initial conditions were put into the code, including the initial position and initial velocity of the mass. The spring constant K was calculated by the equation shown using a T that was calculated using the oscillations in Tracker. L0 was also calculated using the equation shown in the given conditions. The equations to calculate the gravitational force and the spring force were put into the code along with Newton's second law to update the mass's velocity and position. The equations to calculate the kinetic and potential energies were also put into the code to create the model. After everything was put into the code, I hit Run Module to see the model of the spring mass system on the left and the graph of the energies on the right. The model swings in an arc while oscillating up and down like in the video. The red ball represents the observed mass and the blue ball represents the model mass. The model does a pretty good job of predicting the motion of the mass. The red ball is jumpy because the time between the observed position is 20 times longer than each predicted position. The graph shows delta K in blue, delta U from the spring in red, delta U from the earth in green, and all of the energies added together in yellow. The model can also be compared to the analyzed system with a graph of the observed Y positions in red and the predicted Y positions in blue. The model pretty closely predicts the motion, with differences occurring towards the beginning of the video. This may be due to my human error and not correctly tracking the motion of the mass. What does it mean? For the model, the energy principle is satisfied because the energy principle states that the change in energy of the system equals the sum of the changes in potential and kinetic energies of the system. In this case, the energy principle is satisfied because the kinetic, spring potential, and gravitational potential all add up to be 0, which is displayed by the graph with the yellow line. The oscillation period T can be calculated from the position versus time data in Tracker. When the X position data is used, the oscillation period is calculated to be 1.62 seconds. When the Y position data is used, the oscillation period is calculated to be 1.49 seconds. These values differ because they are measuring different things. The X position is the position of the mass as it swings in the arc, and the Y position is the position of the mass as it oscillates vertically on the spring. For this lab, we used the oscillation period calculated using the Y position. Thank you for watching Lab 4.